All right, let's get right into it. You hear about AI all the time, right? Well, today we're going to peel back the layers and look at the one single idea that's at the core of almost all of it. We're talking about the intelligent agent.
So here's a question for you. What do a robot vacuum, a self-driving car, and your email spam filter all have in common? It sounds like the setup to a really bad joke, I know. But the answer is actually super important. What they all share is that they are, fundamentally, intelligent agents. And really getting what that means, well, that's the key to unlocking how most AI actually works.
So what is an intelligent agent? It's actually a beautifully simple concept. It's anything that can look at its surroundings and then do something. That's it. It perceives the world using sensors and then acts on the world using actuators. For us humans, our eyes and ears are our sensors, and our hands and feet are our actuators. For that robot vacuum, its bump detector is the sensor, and its wheels are the actuators. It's just a constant loop. Sense, then act. Get input, produce output. Simple, right? But incredibly powerful.
Okay, so perceive and act is a great start, but it's a little vague, isn't it? I mean, what's its job? What's it trying to accomplish? To nail that down, AI designers use this really handy framework called PEAS. PEAS.
You can literally think of PEAS as writing the agent's official job description. Before you write a single line of code, you have to know exactly what its job is, where it's working, and what a good job even looks like. PEAS forces you to answer those questions by defining 4 specific things: its performance measure, its environment, its actuators, and its sensors.
Let's make this real with the self-driving car example. So for P, performance, what makes it a good taxi? Well, it needs to be safe, fast, legal, and comfortable. For E, environment, where does it work? On roads, with other cars, pedestrians, customers? It's a messy, unpredictable place. For A, actuators, what can it actually do? It can steer, accelerate, brake, flash its signals. And finally, S, sensors. How does it perceive that world? Through cameras, GPS, radar, all that cool tech. See? Once you fill this out, you have a perfect blueprint for what this agent is all about.
All right, so now we know how to write the job description. But here's the thing. How an agent actually thinks and makes decisions can be wildly different. Not all agents are built the same. A great way to think about this is like a ladder of intelligence. Each step up the ladder represents a big jump in how smart and complex the agent is. So, let's start at the bottom and work our way up.
Right at the bottom, the first rung, we have the simple reflex agent. This guy is, well, simple. It operates purely on if this, then that rules. That's it. Think about a basic thermostat. If the room is too cold, then turn on the heat. Or an automatic door at the grocery store. If it senses motion, then open. No memory, no planning, just pure, simple reaction. Now, the huge upside to this is that these agents are incredibly fast and efficient. There's no thinking involved, just pure reflex. But, and this is a big but, they have a major weakness. They only work if they can see everything about their environment all at once. We call this a fully observable environment. If there's a blind spot, if they're missing even one piece of information, they are completely lost. They have no idea what to do.
And let's be real, how often in the real world can you see the whole picture? Pretty much never, right? So that brings up a huge question. What happens when an agent can't see everything? How do you build an agent that can deal with uncertainty and missing information? Well, solving that problem is exactly what gets us to the next step on our ladder. Say hello to Level 2, the model-based reflex agent. Now this agent is a step up because it has something the simple one didn't, a memory. It keeps an internal model, or a kind of mental map of the world. This lets it keep track of things it can't see right now. So for a self-driving car, even if a cyclist passes into a blind spot, this agent remembers they're there. It has a mental picture that goes beyond what its sensors are telling it in this exact moment. So how does it do this? Well, it has a few key components. First, it has its internal state. That's its memory, its picture of the world. Then it has a transition model, which is just a fancy way of saying it understands cause and effect. It knows that if I turn the steering wheel, then the car will move to the left. And it also has a sensor model, which means it understands its own sensors. It knows that if it's raining, its cameras might have water droplets on them, and that affects what it sees. Okay, now we're really starting to climb the ladder. Level 3 is the goal-based agent. This is a huge leap because this agent doesn't just react or remember. It has desires. It has goals.
It knows where it wants to be, and it thinks ahead to figure out how to get there. The perfect example is the GPS on your phone. You give it a destination, that's the goal. It doesn't just react to the next turn, it plans the entire route to achieve that goal.
This is where the agent starts asking questions about the future. It's thinking, okay, what happens if I turn left here? What if I go straight? Which of these paths will get me to my goal? It considers multiple possibilities and chooses the best sequence of actions. This is where things like search and planning come into play. It's no longer just reacting, it's strategizing. But wait a second, what if there's more than one way to get to the goal? What if one way is faster but has more traffic, and another is slower but more scenic? Or what if you have goals that conflict with each other, like get there fast but also use less gas? A simple goal-based agent might get stuck. And that brings us to level 4, the utility-based agent. Think of this as a much more sophisticated decision maker. This agent uses something called a utility function. You can just think of it as a happiness score. It looks at different possible outcomes and gives each one a score based on how desirable it is. This lets it make smart trade-offs. Is paying a toll worth it to save 15 minutes? A utility-based agent can actually calculate that and decide. It's not just about reaching the goal anymore. It's about reaching the goal in the best, most optimal way possible.
All right, we've made it to the very top of the ladder, the pinnacle. And this is where things get really, really interesting, because this final type of agent can do something the others can't. It can learn and improve all on its own. The whole point here is to achieve autonomy. A truly smart agent isn't just stuck with the knowledge its programmers gave it. It learns from experience. It tries things, sees what works, sees what doesn't, and gets better over time. It can actually become more capable than how it started out. So, how does this learning actually happen? Well, you can think of it as having 4 parts working together in a cycle. First, you've got the performance element. That's the agent just doing its job. Let's say it's your spam filter deciding to let an email into your inbox. Next, the critic steps in. The critic gives feedback. That's you, when you see that email and angrily mark it as spam. Then the learning element takes that feedback and says, aha, I made a mistake. It then updates its internal rules to get better at spotting spam in the future. And finally, there's the problem generator. This part is really cool. It's what makes the agent curious. It might suggest trying something new, just to see what happens and gain more experience. It's this continuous loop that lets the agent evolve and get smarter all by itself. Okay, so we've climbed this whole ladder from a simple thermostat to a complex learning machine. Why did we do this? What's the big deal? Well, because understanding this ladder, it's like understanding the blueprints for almost any AI system out there. It shows you the fundamental designs that everything else is built on.
So, let's wrap this up. What are the big things to remember? First, the way an agent is designed, its architecture, defines its limits and its capabilities. Second, intelligence isn't magic. It's built up layer by layer, starting from simple if-then rules. A simple agent like a thermostat is fast, but pretty limited. A complex agent like a self-driving car needs models, goals, and learning to handle the chaos of the real world. And maybe the most important takeaway is this. If we ever hope to build AI that is safe, reliable, and beneficial, we have to understand these core building blocks first.
And that leaves us with a final, really important question to think about. As we get better and better at building these incredibly smart agents that can learn and plan and achieve things, the question stops being, how do we build them, and starts becoming, what should we tell them to do? What goals, what utility functions are we giving these systems that will soon operate on their own? Figuring that out, well, that's the real challenge for all of us.